this session, we would be studying about modelings of small MOSFETs. We have been studying about long channel effects, like long channel MOSFETs, where we have designed like MOSFETs with larger lengths and widths. So in today's lecture हमने ये देखना है कि this video session हमने ये देखना है कि new अब MOSFETs का size कैसे reduce कर सकते हैं, and what would happen if you reduce the size of of a MOSFET. हम बेसिकली MOSFET का साइज रिड्यूस करने के लिए करते क्या है कि हमने अपने जो चैनल लेंथ्स हैं या चैनल विड्थ्स हैं, हम बेसिकली उसको क्या करते हैं, श्रिंक करते हैं, उसको ऑब्वियसली रिड्यूस करते हैं. मॉडर्न जो CMOS ICs हैं उसमें जो चैनल लेंथ है बेसिकली वो अप्रॉक्सीमेटली अराउंड 12 नैनोमीटर और इवन लेसर तक डिज़ाइन किए जा रहे हैं. Channel length is a constant quantity because it is process dependent, while we can only change or we can modify the width of our channel. And for that to understand, we have to discuss what are scaling theories or what are the effects of scaling when we reduce size of MOSFET. So for that we have to cater about we have to tackle some different parameters which are like width. You obviously know that this is our channel width. AG is basically area of gate. C oxide represents the oxide or capacitance of oxide material. CG represents the capacitance of gate area, and there are beta resistance, and then we have a parameter which is threshold. And obviously VDD can be reduced as well. Similarly, we have VGS, that is gate to source voltage. We have ID, which is our current, and P, which is obviously which shows the power dissipation. So to understand this theory, we have to study or we have to derivate some of the equations, and then we can link or we can link to our this small modeling theory. So for that we have to study how we can design a small MOSFET, a MOSFET with reduced size, and then we have to study what would happen to the resistance, capacitance, current and power of the MOSFET, and how can we achieve same current or same resistance while we are reducing the size of a MOSFET. So for that we have to obviously derivate some of the equations, and we have to relate with the original MOSFETs. So scaling theory के लिए जो हमारे पास critical dimensions हैं, or we know that they are W and L. We have width and length. This width is our channel width, and this length is our channel length. And if we have to design a reduced size inverter, we assume both sides are reduced by a scaling factor which is given by some constant. Assume we reduce both factors by S which is greater than 1. So we are reducing these our W and L with a scaling factor that is given by S, and this S is basically this S is you can say that S is a scaling factor. So this S is our scaling factor, and we can say that we have to find somewhere we have to find the aspect ratio. aspect ratio is normally like W by L. So we can say if we have to find aspect ratio, the updated aspect ratio, that is like W star by WL, this will be given by updated values, like this will be W by S and this will be like L by S. So we have our updated values as like W by S and the other one is L by S. So if we solve this expression, these two S cancel out each other, then we will be left with W by L. So we can say that the aspect ratio does not change. It remains original, like it remains the same. So we have this original quantity that we didn't change. And we have to find the gate area. Like if we find gate area, it was originally designated with AG, and we have to find this was obviously equal to W into L. This gate area was W into L. Now we have to find the scaled area that we scaled, like after this width and length updation. We have now a scaled gate area, which is given by scaled area is AG star is equal to like W by S into L by S, and this is equal to WL divided by S square. And if we like simplify this in terms of AG, this will be equal to AG divided by S square. So like our whole area of MOSFET reduces significantly. So we have reduced our area significantly when when we change the size from W by L, like from W to W by S and L to L by S. So if thickness of new MOSFET is also decreased, like we say that if thickness like oxide thickness is also reduced by S, obviously that is same factor, then we know that the capacitance will be affected. So we can say that then oxide capacitance is given by C oxide, which is equal to epsilon oxide divided by T oxide. But now we have T oxide star is equal to T oxide divided by S. So we can say that the updated MOSFET capacitance, like the oxide capacitance, will be equal to epsilon oxide divided by T oxide divided by S. This will be equal to epsilon oxide divided by T oxide and multiply by S. And simplifying this expression in the form of this original like C oxide, this gives us C oxide multiplied by S. So we can say that the capacitance is like increased with the factor of S. And if we have to find the gate capacitance, it was originally given by Cg, which is equal to C oxide multiplied by Ag. Now we have already found the value of Ag, and we have already found the value of C oxide. So we will put both these values here. So the updated Cg can be written as C oxide steric multiplied by Ag. C oxide is given here, like we have to multiply C oxide multiplied by S, and we have Ag, which we have already calculated earlier. This was equal to Ag divided by S square. So if we solve this expression comes out to be C oxide Ag divided by S. So you can observe here, like the updated gate capacitance will be equal to Cg star is equal to Cg divided by S, that is reduced by a factor of S. So the next quantity that we have to find is device transconductance. So this was given by beta, which is equal to K bar W by L. So we have found that this ratio doesn't change, that remains the same, but this quantity can be updated. Why this quantity is updated? Because we have Kn, K bar is equal to mu C oxide, and this mu is constant. This doesn't change because हमारे पास ये जो म्यू ऑक्साइड है ये बेसिकली रिप्रेजेंट कर रहा होता है हमारी लाइक मोबिलिटी ऑफ carriers. So we can say that our updated K bar will be equal to this will be equal to mu C oxide square, and we have already found like this is equal to mu C oxide and S, and this can be written as K bar star is equal to K bar S. So this is updated with a factor of like S, and we can find this updated beta here now, that is given by beta star is equal to like we can write it first here like W by L, and we can write K bar S W by L. So our normally these two are constant, like W by L ratio is constant, and this factor is increased by like S, and I can I can write it as S beta, because this vector is like this vector and this vector is represented by our beta here. So our updated beta is given by this, and next factor which we have to find is drain and source resistances. For drain and source resistance, like we obviously for the new device, drain and source resistance for new device, the drain and source resistance for new device is given by like R star, which is equal to 1 over beta star VDD minus VT. So we have known this value here, we can replace it 1 over beta S and VDD minus VT, and if we want to write it in expression of R, that will be given by like 1 over S into R here. So we can say that when we change our device, it will result in an updated resistance, like its resistance will be reduced. what effect we will have on voltage as well. So the next thing we have to study is, like, we have to observe is what effect we will have when we have a voltage scaling after this, reducing the size of our MOSFETs. So if we perform voltage scaling, what would happen? Like, for voltage scaling means we reduce our VDD voltage, the updated VDD voltage, by a factor of S, and the threshold voltage VT by S. Then what effect will have on resistance? The resistance was given by R star is equal to 1 over, it was what we found is 1 over B star into VDD minus VT. If we put the values here that we just found out to be, and then we have just assumed VDD will be 1 over VDD by S and VT by S. So this will be equal to 1 over S beta and VDD by S minus VT by S. So if we solve this expression, we will get 1 over beta VDD minus VT, and this is equal to R. Strangely, what we observed is कि जब हमने अपने MOSFET को स्केल डाउन किया, स्केल डाउन करने के बाद हमने ये ऑब्जर्व किया कि हमारी रेजिस्टेंस जो है बेसिकली वो रिड्यूस हो जाती है. But obviously what we would like to do is we have to there could be a reason कि हम अपनी रेजिस्टेंस को सेम रखना चाह रहे हो. So for that हम ये करते हैं कि अपनी वोल्टेजेस को भी कम कर देते हैं. जब अपनी वोल्टेज को कम करते हैं तो हमारी रेजिस्टेंस जो है बेसिकली that will be the same resistance as we had earlier, as we had the resistance effect जो कि हमारे large MOSFET में था. So to see the effect of this resistance on current and power, we can observe different voltages. We can have voltage like VDS, which will be reduced to VDS by S, and obviously we have VDS that is given by VGS by S. Obviously we want to study the power and current. We know that drain current in saturation region is given by ID. It is obviously that is equal to, if I write it in an updated form, that is equal to beta star divided by 2. Then we have 2 multiplied by VGS star minus VT star. We have VDS star minus VDS star square. This is expression for ID and current in saturation region. If we put the values here, the assumptions and the values here, we will get S beta by 2. Then we have 2 into this is VGS by 2 minus I'm just making something wrong here. हमारे पास ये वैल्यू जो आएगी ये S होगी और this will be VT by S, and then we have VDS by S minus VDS by S, that is obviously square and S is square. So अगर हम ये वैल्यू सॉल्व करें, ये एक्सप्रेशन सॉल्व करें, तो हमारे पास जो फाइनल एक्सप्रेशन आती है that is ID star is equal to this expression comes out to be 1 over S into ID. It means के जब भी हम लोग अपनी voltage reduce करेंगे, like we have reduced our VDD, we have reduced our like VDS and obviously the gate source voltage. जब हम अपनी ये voltages reduce करेंगे, ये सारी voltages जो हैं, तो हमारे पास जो current है basically वो भी half like वो भी like with a factor of S reduce हो जाएगी. And we can also find the power, like power will be equal to P is equal to, like obviously we have to find this formula VI. We can put the values here. We have P star is equal to, this is VDS by 2, VDS by S multiplied by ID, and that is obviously equal to ID by S, which we have found to be here. And then we have VDS and ID divided by S square, and we can also write it like P by S square. It means के हमारी जो current है वो with a factor of square reduce हो गई है. So we can say that this is a motivating factor to reduce the voltage as we reduce the device size. Like हम जब भी device का size reduce कर रहे हों, जब भी हम लोग ये काम कर रहे हों कि अपने devices को small size में convert कर रहे हों, तो it means के this shows के we have to reduce our voltage as well. So we can say that it is a motivating factor for voltage reduction. So this is a motivating factor when we reduce our voltages in case of small MOSFETs. So that's it for this session. I will see you in next session.